try to get the copies emailed to you, but I will continue to update them, so it's better that you can just get them online. So if you can do a Google search of me, Pete Schwartz, Cal Poly Physics, and go to my department web page, or you can go through Cal Poly. There's a bunch of ways to get to my Cal Poly web page. And then the very first thing at the top says, do you want to get these energy resources? You click on that, and then it'll take you to a web page and a document that you can download it. And when you open it up, it'll have a spreadsheet where you have different topics on the side, and then it'll have your reading assignments, and then it'll have videos. Now, you're not a student in my PSC 320 class, so these aren't your assignments. But if you're interested in any given topic, you can go to these web pages and read about it, or you can see these videos. And I'm very interested in what you think about them. If they work for you, send me your feedback. Thanks.
Thank you. So we're going to shift gears now. That's probably more than talking so much about the basic science. We'll start to talk about impacts in alternative energy sources and similar topics. So let me introduce Louis Pitelka. Luke moved to Cascadero 2 to 3 years ago, and he's been a wonderful asset in our community. He's an active participant in an endeavor called NEON, which is the National Ecological Observing Network, and he will explain a little bit more about that, and then tell us about the birds and the bees and the flowers and the trees. Luke?
Thank you. All right. Actually, I'm not going to talk a lot about the birds and the bees, but I will talk about the flowers and the trees. So I'm going to tell you a little bit about what kinds of effects we can expect from climate change as it happens for the ecosystems of California. I'm going to try to focus a little bit even more on San Luis Obispo County, but basically what I'm going to tell you applies almost anywhere in the world, or probably everywhere in the world. I'll say a little bit about agricultural effects, but focus mostly on natural ecosystems. So, I don't know. Yeah, you're right. There we go. Good. Oops. Perfect, yeah. So I'm going to start out with some simple principles or things that we've known for a long time that lie behind most of what I'm going to say. So the most important thing is that climate is the most important factor determining where native plants and vegetation types occur, and also to some extent where agricultural crops are grown. Humans can manipulate that, especially with irrigation, but it's still, I mean, we don't grow bananas in British Columbia, so that's an example of how climate determines that bananas can't grow in British Columbia. So if that's true, then as climate changes, we should expect changes in the distribution in where plants and animals occur naturally. And so what we can expect is that climate zones will shift poleward towards the North Pole and the South Pole in the northern and southern hemisphere, and they'll also shift up in elevation. And in order to survive and thrive, native species will have to keep up with that shift in the climate zone, because we've already said that where they occur is determined by climate. So they will actually have to move geographically. Their distributions will change geographically. And species that can't move for one reason or another, or don't move, will either do more poorly, depending on how drastic the climate change is, or they could gradually die out. The same principles apply to agriculture, except farmers may have ways to adapt. They can irrigate if they weren't previously irrigating, or they can change varieties, or there are a variety of things they could do. So I'm going to give you just a few quick examples of the kinds of agricultural effects that we might expect. All of them are a little more complicated than just the fact that it's going to get hotter, and the plant might not like that. So this is an example of a factor that determines the productivity of almonds, apples, and walnuts in California. And it turns out for these species, which can grow in fairly cold areas, that they actually require a certain amount of chilling during the winter in order to produce good fruit crops. And what this shows, where'd the pointer go? Pardon? Oh, yeah, I think actually this is the red. Okay. So what's plotted here is the number of chill hours that are occurring in these different areas of California, and this is sort of the historical average up here in these different areas. And then the other two bars are projections for a lower warming range and a medium warming range. And basically, the plants, in order to produce good fruit crops, have to get above this level. And so what you can see is with warming, there are going to be fewer cold nights and cold days in the winter, and the potential exists that fruit production from these species, where they grow now, would go down drastically. Here's an interesting example where it has nothing to do with the plant, but rather with a pest for the plant, the cotton pink bollworm that attacks cotton. And right now, the suitable range for this species is confined to down here. So the cotton that's grown up here, well, there's a little spot there, is pretty much doesn't get affected by that species. But with climate warming, the potential range of this pest is going to expand drastically, and so it could become a serious pest in areas where it isn't a pest now. And then we all care about the viticulture, the wine, the grape industry, and this is showing some projections that almost seem too drastic to me, but it essentially shows for three different areas, or two different areas of California, and then total for California, some projections of how much the suitable area for growing grapes for wine will decrease with climate change. And there are two different climate models here, and the GFDL and the PCM. And then for each of those, there is a projection by mid-century and the end of the century. And what you can clearly see is that the numbers are quite alarming in terms of how large they get. So for our area, this one's predicting a 97% reduction in the amount of suitable area, unless the farmers or the ranchers, whatever you want to call them, what are they called that grow grapes? Vintners, yeah. In some places that may mean if they don't irrigate now, they'll have to irrigate. Another possibility is they change the varieties that they grow to varieties that are more tolerant of warmer conditions. So Santa Barbara County won't be so famous for Pinot Noir anymore. It'll have to change over to Zinfandel or something. So we can't really say, without going into the possible adaptation means, exactly how much production would decrease, but it's obvious that the projected kinds of climate change that have been made could be serious, have serious implications for that industry. And then John, I think, covered this, so I won't go over it again, but it's basically just to say that our current system of providing water, both drinking water, this is Hetch Hetchy Dam in the Sierra that provides the Bay Area with a lot of water, that our current dam and reservoir system depends upon there being a snowpack that melts very slowly and releases water, because these dams can't hold all the water that comes in a full season of snowfall and rainfall. And so if we're getting much more rain during the winter in the Sierra and at higher elevations than we do now, then most of that water can't be held in the reservoirs if it all comes at once. And so there will be a whole lot less water for agriculture and other uses. And that says nothing about whether rainfall is going to get more or less as a result of climate warming. If rainfall is less, we're getting conditions like we have this year, then it'll be even more serious. So let me turn now to what I'll spend more time on, and that's on the effects on the distribution of natural vegetation and also of native species of plants. So California has a lot of microclimates, a lot of variability in climate and temperature and precipitation that are caused by latitude, by elevation, by distance from the ocean. And you can basically see that. This is a vegetation map of California with some of the, this is one classification of vegetation here. And I have to apologize, but every map I show you will have a different classification of vegetation. And I don't know, it's impossible to reconcile them exactly, but I'll try to point out, you know, what we're talking about. So oak woodland, we have a lot of that around here. We have a lot of chaparral, and we have some grasslands, and we have forest, of course. So what you can see, for instance, there's a latitudinal gradient. This is desert down here. There's a lot more forest up here. You can see a gradient sort of east-west, which has to do with distance from the coast, but more importantly, a lot of the variation is determined by mountain ranges. So that's what the current natural vegetation is. And this is a set of slides that show projections from a model that takes the output from global climate models and puts it into a model that attempts to predict where plants will grow. And it shows for 1990, 2020, 2060, and 2100. And I don't want you to look at a particular spot and say, well, that's going to happen. That's something we can't do, just as I think Ray pointed out, that you can't predict exactly what's going to happen at any particular spot in California or in San Luis Obispo County. But what you can see is that big changes occur. And so a piece of advice I heard from a climate scientist, a famous climate scientist, a number of years ago, is when you're looking at the projections of a model that's attempting to predict the future, don't take it literally. In other words, all right, so at this particular spot it says it's going to change from this to something else. That's what's going to happen. No, that's not necessarily what's going to happen. But take it seriously. These are showing the sensitivity of vegetation to climate, and you're getting big changes. And just one in particular that I'll point out, because I'll come back to mention it again, is look at the blue, which is alpine meadow. It almost completely disappears from the Sierra. Now, for those of you who have camped or backpacked in the Sierra, know the alpine meadows are one of the most beautiful features of the Sierra, and those are going to essentially be invaded by forests over time. There are two reasons why there's a gradual projection changes over time. One is that the climate is continuing to change over this time and warm, unless we do something really quick. And the other is that although it's not built into the models here, is that plants will take a while to actually migrate. If we're saying that alpine communities will gradually disappear, what this is telling you is that this is how suitable the area is for alpine communities. But it may take many decades for plants to die out and for trees to migrate in and grow up into forests. This just summarizes some of these data and shows you how much of a change in area compared with the current or recent past situation will occur with these different kinds of vegetation and with 3 different warming ranges. And you know, we could talk about any one of these in more detail, but the important point is you're seeing huge changes potentially. And here's again alpine area and subalpine forest with in the highest warming range almost 100% decline. And then increases in certain kind of forest, increases in grassland, desert, depends a little bit on the climate range. So again, the point is not to look at the details, but see that we're talking about big changes in California. And this is, I discovered this fairly recently. This is from a report that I guess was commissioned by the county here. And my final slide will give you a link to it if you're interested in it. I actually found it on the San Luis Obispo city website, or a link to it. And it's just showing, again, I promised you different categories here, and I can't even read them there. And I won't, basically there are two of them, subtropical shrubland and what's the other one? There are two shrublands there. Can somebody read it for me? There's subtropical, and temperate shrubland, which are some of these colors here, which are chaparral. And you can just see that there are, from the current to, and I should say that this is two different time periods. This is more like closer to the middle of the century and later in the century. These are three different climate models that are used. And you can see that there are changes. So I wouldn't look at any one spot and say that this is what's going to happen, but again, it's showing the sensitivity of the vegetation in this area to climate change. Okay, another really big concern for us around here and lots of other areas of California is fire. And this just shows you a projection of the probability of a large wildfire in different areas of California, larger meaning more than 200 hectares. And so this is the historical average, and this is a lower warming range and a medium warming range. And it's pretty obvious that there's huge increases in the probability of fire over much of California, including our area. And this is a plot of actual area burned over the last, well, that one shows about 60 years. And again, you can see that there's lots of variation. Ray pointed out the same sort of phenomenon. This is the black dotted line is a 5-year running average, whereas these are annual amounts burned. So we know that there's tremendous variation from year to year, but we're beginning to see a clear trend in the data. So this is, if I can get it to work, is actually a model that, results of a model that gave us those results. But this is now, this is actually going to be a dynamic model in that it's going to run for about 200 years, and you're going to see colors change on the map. And red is areas where there's fire, a lot of fire. And so you can see some other things. Here's the blue representing the alpine, and so over time you'll hopefully, if it works, see the amount of blue disappear. This is desert, and there are going to be changes that probably are because the particular climate model that was used predicts increases in the amount of rainfall in California. And so I think a lot of this becomes grassland. But you'll see other changes that might include forests at lower elevations. Let's see what happens here if I can get it to go. There we go. And you'll see some big fire years, and I think they'll become more common over time. You know, it's not too much red that you're seeing. There was a big one. And changes occurring here. There was I don't know if that actually happened in that year or not. Probably should have, because it should be based on. So, you know, the amount of blue is getting less. There's changes occurring out there. Lots of different things determine how much fire you get in a particular area, and some of it's not necessarily intuitive. And I've actually never figured out, you hear it both ways from experts. You know, if you have a really hot, dry year, there are going to be bad fires. If you have a really wet winter, you'd think there are going to be less fires. There's more plant growth. There can be more fires, or worse fires, so it doesn't always make sense. Okay, so those are my comments about vegetation. As sort of vegetation is composed of many different plant species and different areas of characteristic vegetation. Ours being the different vegetation types in our area, especially oak woodland, mixed oak forest, chaparral, grassland. Now I want to focus more on species, at the species level, and what are the threats to biodiversity. And so I'm going to, in a series of slides, going to list some of the major threats posed by climate change for biodiversity. So one of them, and so what we're talking about is the first one is the disappearance, literally from the face of the earth, of particular climatic zones. And where this is likely to occur is at the poleward tips of continents. So here's a map of the earth. And so what we're saying is that up here, it's tundra. And if it warms, then tundra will gradually get replaced by boreal forest, by conifer forest. Or down here, or here, the same sort of thing will happen as climate zones shift to the south. And where the big threats to biodiversity are not up here, because the continents in the northern hemisphere extend closer to the North Pole than, well, this one extends fairly far, South America, but Africa and Australia don't extend as far south. So they're more like about this area, their tip. And so up here, the biodiversity is fairly low. And so although we will lose a lot of tundra area over time, the total number of species that could go extinct, that no longer have a place to live, isn't that large. Whereas I don't know how many people are aware, but the southern tip of Africa is one of the most diverse and unique floras in the world. And to some extent, the same thing is true of southern Australia. Here, when you get down to Patagonia, it's a little closer to being like tundra, so it's not as rich. So in southern Africa, in South Africa, they're actually quite concerned about the future of their extremely unusual flora, where almost all the species don't occur anywhere else in the world. And so what's going to happen to them in terms of their natural habitat? A similar sort of thing is going to happen in alpine habitats. And so I've already talked about the disappearance of alpine vegetation in the Sierra because because of the warming. And this sort of illustrates, this cartoon illustrates what we're talking about. So we know from many studies over many decades that when you go up in a mountain range, you can see different species that grow at different elevations based on the climate and what they're adapted to. And so you can imagine that in the present climate, there's a species that occurs here at this elevation and another one that occurs there. As it warms, the climate zones will shift upward. You know, the conditions here that this is adapted to will now be found up here, and here it'll be too hot. And so you predict that the species will move up in elevation. Well, for species A, their climate zone doesn't occur any longer. They would require mountains that are higher, and that isn't something we can do much about. So the suitable habitat for species A would disappear entirely, and species B would be confined just to the mountaintops and be nowhere near as widespread as it was before. So because of that, we are expecting the loss of a lot of biodiversity in alpine floras all around the world, not just in the Sierra. This lists a couple of more places where we can expect to see biodiversity losses. Coastal wetlands are a problem because with sea level rise, they'll get inundated, and often there isn't any place for them to reestablish because it's all covered with human habitation and settlements and everything. So that's a concern. And then there are plants, although I said that climate is the most important factor determining where plants grow, that's not true for every single species. There are plants that are adapted to particular soil types, like there are plants that like limestone soils, and around here we have a lot of serpentine outcrops. And serpentine has a distinct flora of plants that don't occur elsewhere. And a lot of people, they have beautiful, serpentine has beautiful wildflowers in the spring. And so a plant that's adapted to serpentine, when the climate changes, it may no longer be able to live on that particular outcrop. So the question is there serpentine farther north, or is there serpentine farther higher in the mountains for them to move to, and can they do that? And then here are a bunch more examples of the kinds of species or the factors that will determine whether species go extinct. One is that there may be a lack of suitable habitat due to land use changes. That's true for native species, so we've replaced forests and chaparral and grassland with agriculture and our habitations and things like that. It's actually one of the concerns about viticulture and wine growing is that a lot of the areas that could be suitable for wines have been taken over by settlements and other things. Fragmentation of habitat and new barriers. So species, in order to keep up with their climate zones, are going to have to migrate, which they are capable of doing. We know that from, for instance, the ice ages, when as the glaciers melted, species were able to invade areas that were previously covered by ice. And if a volcanic island suddenly appears out in the middle of the ocean, over time, plants and animals start showing up that had to somehow get there over the ocean. So we know that species can migrate, but changes in the land cover caused by humans and barriers, everything from roads to cities to whatever, will interfere with the capacity of species to migrate. And then the other factor that's related directly to that is how fast species can migrate. And it actually turns out, if you look at how fast climate's going to change, and what that means in terms of the climate zones, species would have to migrate over long periods of time at the rate of about 1 meter per hour. If you assume that climate change, that climate zones shift by about 1,000 kilometers over 100 years. And that's about what we're expecting. So there are species that will keep up with this. I was told not very long ago by a mammologist in Michigan who has been studying small mammals in northern Michigan for many years, that they can migrate at about 1 kilometer per year. Now that's not actually enough to keep up with this, but these are little tiny animals, and so that's pretty amazing that they actually are moving northward at that rate. And then another problem can be lots of species are dependent upon other species for their existence. And so if both of them don't migrate at about the same rate, then one of them can essentially lose the species it's dependent upon and won't be able to survive. And it has nothing to do with climate change, but that's what the big problem for monarch butterflies, because there's no milkweed around. Nobody's planting milkweed. It's a weed to many people. And so the species that they depend upon, where they lay their eggs and the caterpillars feed, there aren't enough of them around anymore. So the fact that their habitat in Mexico is being destroyed isn't the only thing. Their habitat in the United States is being destroyed too. And then a final threat to biodiversity associated with climate change is that there are a lot of weedy species that have come from other continents that are major weeds for us. You know, Russian star thistle around here is one of the worst and you can possibly imagine. But all over the United States, we face problems from invasive species. Invasive species are really good at migrating, and they're better than our native species. And so when forests in one area start to die out, who's going to get there first? Well, the invasive species that we don't want, not necessarily our species. So that's another threat in terms of the long-term viability of many native species. So summarizing, in terms of what's at risk, rare species are, I think, by definition at risk. That seems intuitive. And rare species are those that only occur in a few locations, or those that have very low numbers where they do occur. Species with very narrow overall geographic distributions are at greater risk, and I'll show you why in the next slide. I already mentioned migration capabilities, special habitat requirements, and dependencies on other species. So this is just an illustration, basically, of how how we determine or estimate the risk that different species face, and also vegetation types. And so the title here is Calculating Climate Envelopes, and by a climate envelope we mean the range of climatic conditions over which a species can occur. And so this just gives you an example that's approximate, but it's a pretty good example, and it shows 3 different species: giant sequoia, balsam fir, and another species, it's a conifer, toria in Florida. And I selected these out of a large number of species to illustrate the differences between what happens to a narrowly distributed species, these two, and a very broadly distributed species, balsam fir. And I'll just point out here that you might notice how far north it goes here around Hudson Bay, because the next slide will show you the differences. And so what you do is you look at the climate conditions that exist across here, and that basically defines the climate conditions over which balsam fir occurs. And this defines the climate conditions over which giant sequoia occurs. And you can plot it against, say, temperature and precipitation, although when scientists do it, they actually do it with a lot more specific information, like instead of average annual temperature, they'll want to know the average high temperature in the summer and the average low temperature in the winter, and also the seasonality of precipitation. So it actually gets much more complicated. But if you just do it this way, you can see this is showing that on this axis, balsam fir occurs over a wide temperature range and pretty wide precipitation range, whereas the other 2 species don't. So then you say, okay, the climate's going to change. Where do those climatic conditions occur under the new climate? And so this was a very simple analysis, and I don't want you to go home and tell somebody that giant